So the internet communication can be decomposed in the 5 layers. So we have applications layer on top. This is what we'll start with, applications. And this means we exchange messages between processes. We will find many protocols and systems there, like mail, like HTTP for web, like the DNS or name resolution, etc. Next layer, if you go down the stack, that's our transport layer. There we find protocols like the classic one, TCP, UDP, but also SCTP, QUIC, etc. This is, among others, for multiplexing of different applications on a host. So if you think of a host, this is our interface to the networking. We have many different applications. And what we have are our service access points. And now you connect a process to one of these service access points. And if data comes in, these protocols, transport protocols, for example, TCP, they know, okay, depending on the port, I will send the data to this service access point, and then the process can consume the data. Then we have very prominent big player network, our IP protocols, version 4, version 6. They're used to move the packets around the network. They have these global unique addresses we need to forward the packets. Underneath this, we have the link layer, MAC layer sometimes called. There are some differences between what the MAC layer has, a data link layer, than some other convergence protocols, etc. But we can simply call it the MAC layer, data link layer. This is important to move frames or data packets, they're called frames here, across a single link between two hosts. So Ethernet or wireless LAN from your laptop to the access point, etc. And then we have the physical layer. The physical layer is quite important then to translate our bits, our bit stream, into signals that can be transmitted, copper wire, wireless, etc. Again, this is quite short on this topic, but that's okay for here. Because we will focus on the internet, higher layer protocols. So what is the important part here? Many years ago, Steve Deering talked about the protocol hourglass. What does it mean? The context of the internet, everything runs over IP. And there are many advantages and disadvantages for this. And underneath, we can have many different protocols. But everything goes through this narrow waist of IP. Maybe it's a bit wider now with different versions, so IP4, IP6, and there were some other ideas. I mean, this a bit wider, and maybe there are some problems associated with this. We'll come back to it. So this, most people say, is a brilliant idea. Why? If we have a single protocol here, this means we have a way for global addressing. We have the IP address. So we know exactly what does it mean if a packet, I write IP version 4 because 6 is a bit too long, goes to a computer that's 129.13.42.17. Where does this end up? Globally unique address. Because if you have different addresses, well, that makes life way more complicated. What else? We isolate end-to-end protocols from network changes. We have here end-to-end protocols, up here, end-to-end. We have a lot of applications on top of this. So no matter what's going on here in these low layers, if I'm in a Wi-Fi network, if I'm a classical Ethernet or whatever, we don't care. Because everything goes through IP, and IP hides all this. So we don't see what's going on down there. So that is quite nice. So if we change the network, doesn't matter. Well, it doesn't matter. We'll talk about this as well. This also helps maximizing interoperability. If we agree upon this single protocol, we know for all the higher layer protocols and the lower layer protocols what to attach to. So We know exactly how these interfaces should look like. And if you follow the rules for these interfaces, it's no problem to invent your new protocol X, attach it, or your new fancy protocol Y up there. As long as you can talk to IP, it works. We have few interfaces, so we do not have many protocols on layer 3. We have one IP, okay, different flavors, 4 and 6, but so we don't have too many different interfaces. And one of the most important parts is we do not expect that much from the underlying networks. What does this mean? We do not expect that much. Now, let's assume you have a layer 3 protocol that says, okay, I guarantee to you a maximum delay of this and that. So that would be the protocol X guarantee something. This would mean that, okay, we cannot use classical internet because this doesn't guarantee it. Asynchronous is also a stupid idea, etc. Radio is also a stupid idea. So if we guarantee certain delays, whatever, only few protocols can be used. But if you go follow an approach like IP, which is what we call best effort, that means I try my best. I cannot guarantee anything. I try my best. Then this also means, hey, I can use whatever is there, even a pigeon transporting data. Because I do not guarantee anything, well, that means I do not guarantee anything, but also I have no special requirements for the underlying networks. So that's of great help. But disadvantage, I can also not offer any guarantees to higher layer protocols. This will cause some problems, and we will see some of the solutions. So if I do not guarantee anything, great, hey, I can use whatever's down here, but what happens if you need something? For example, high reliability, ultra low latency, real-time remote control of autonomous vehicles or whatever. Then we have a hard time using classical IP over whatever network is there. So there are some advantages and disadvantages coming with this idea of this hourglass shaped protocol stack. Everything runs over IP. What else? We have to implement the protocols, and typically the lower layers, physical always, but also link layer is done in hardware, also network layer and some other functions typically done in hardware, especially in high-performance routers. The major so-called data path is done in hardware, and only few parts in signaling, additional information, etc. may be done in software. For the higher layers, transport, application, this is then all software. We already learned a bit about this encapsulation. Now let's have a look at what typically happens in our networks. It's not that abstract anymore. So if we have an application like HTTP with user data, so I want to have this page, etc. The application layer adds a header, get this and that page, and then we will give this via an interface to our transport layer. There's still the header and user data in there, but now this is all together user data from a TCP viewpoint. So we have a TCP header there, among others. We have a so-called port, so we know which process to address. This is done for multiplexing and demultiplexing. This again forms the user data for IP. There, among others, we have the IP address. That means how to address an end system. This again is all the data here for our Ethernet. Typically something, for example, up to 1500 bytes. So that's all the user data, and then we have an Ethernet header, and that gives us the MAC address that, for example, connects an our system with, let's say, an access point in a wireless case or the switch, etc. So this is the encapsulation if we have a look at the Internet protocols. What else do we have to look at? Because we are still in this process of what do we need? What do the standards say? How do we organize our communication system? So we learned we have layers have to communicate. Now we learned, okay, they communicate forms of messages and then adding something and exchanging this virtually with their peers. What is the content? We also have to define this in our protocols. If we look closer into the data, then this is something you should be familiar with. We have a data packet specified in a standard in the internet world called request for comments. These are more or less the standards. And this example, TCP, standard from the early 80s. TCP, the first work started in 74, so in the 70s. So it's pretty old, but it's still one of the protocols used in the internet. So you can imagine, okay, today's applications, protocols from the 70s, 80s, we'll discuss this. But here you see exactly, there we have our ports. And the standards have to define, okay, the destination port goes from this bit to that bit. And then we have some more sequence numbers and acknowledgements, and we have certain flags, etc. So the protocols define precisely the usage of certain bits in a header, and when then the so-called payload follows. The term payload indicates this is something where you, originally pay for. So that's one of the settings for TCP. Then you have the same for IP, etc. So we need standards. Many people don't like the standards, but we have to follow them precisely because otherwise it simply doesn't work. You cannot simply redefine a single bit. Big discussions if you do so, and most likely your systems will not really be interoperable. Communications without standards, that's quite difficult. So if you have your oven, microwave, cooking, whatever, and you want to make it smart, you may add a controller. And this controller, has to be able to talk internet. Why? Because you want to attach it to some cloud infrastructure, want to access the status of your oven via an app, etc. So that means you have to integrate this TCP/IP protocol family in your controller. Otherwise, it's quite difficult. No one will understand the controller. So we need the standards. And if we do not use the same standards, things like this happen. How does this fit? Well, in computer science, what we do is we write a wrapper and then everything fits somehow. In real life, we need an adapter. And then we can adapt, these different systems somehow, and then it will work. And additionally, we have to take care of voltage and all these things. But standards are important because without standards, no interoperability. So that's the important part. And as our communication systems should work worldwide, we need worldwide standards. We cannot live with a German-only standard or a French-only standard or whatever. So now it works in the internet, but why? There are different approaches to standards. There are pretty closed standards, but the success of the internet is based mainly on the idea that the standards are open and that a lot of the implementations are open source. There are also closed standards, very successful closed standards, but it makes life much more complicated. So, open standards allow for fast and broad take-up of solutions because you just look at the standard and you implement. Maybe you find out some problems, some bugs, etc. You can feed back those problems to the community, etc. So open standards do not necessarily require that the implementations are all open, but you should follow certain interfaces, etc. So if everything is open, open source software, yes, that makes it easier. So in the internet world, all the standards are open, and a lot of the implementations are open source, and this helps a lot. This is not true for all the standards. There are also standards that are not open, still successful, but for the majority of the standards, especially in the internet world, this openness helps a lot. Who is doing the standards? Well, we have many different organizations. Well, let's start from the bottom. If we talk about the internet, we'll have a closer look in a second. There's the IETF. The IETF, the Internet Engineering Task Force, they talk about everything around the internet, IP and HTTP, etc. Then you may be familiar with IEEE, Institute of Electrical and Electronics Engineer, and they, for example, they do all this wireless LAN stuff that, okay, how is this newest wireless LAN 802.11, whatever, AXB, whatever standard defined? And this is pretty complicated. Those standards today easily cover thousands of pages. Then we have some more bodies, like, for example, the World Wide Web Consortium, talking about HTML and those protocols. The International Organization for Standardization, ISO, they did not only this model, but they have many other standards for many purposes. Not so much in the internet world, but in many other things, like how does a sheet of paper look like and all these things. The ITU also come up with standards, coding standards, classical telecommunication, and then we have consortia like 3GPP. They do a lot in the cellular telephony, many of the standards there, and so on. And then there are also many alliances also doing some standardization, harmonizations of standards. But let's focus on the internet world, just to mention some more that you heard of them. We have the Internet Assigned Numbers Authority, we have ICANN, Internet Corporation for Assigned Names and Numbers, and some more regional internet registries. So what do? Someone has to decide that whatever .de is a way of, structuring names for, in this case, accessing resources. Well, then we know, whatever our university .de somehow belongs to someone that takes care of DE, this ending for Germany, or .com, or whatever. And someone has to decide, whatever can be entered here, and how does it work? We'll come back to all these things. Someone has to take care about the IP addressing, because if we have 4 bytes for the classical IP version 4, but how do you distribute them also for IP version 6? Where do you register your name? Or can you just come up with an arbitrary name and say, okay, I like whatever? Or can you just pick any arbitrary IP address? Well, you can, but this will cause problems and maybe no one finds you. So you have some more authorities, organizations organizing all these addressing schemes, registration, etc. And we'll come back to this ecosystem later during the course. So let's have a short glimpse into one of the major standardization bodies, the IETF. And the IETF is pretty much different from, let's say, the industry alliances or part, at least, governmental standardization bodies. The idea here of the IETF is, well, to make the internet work. And it work better by producing technical documents that are of high quality and that are relevant. And those documents then influence the people designing, using, managing, etc. the internet. The community, and this in contrast to, let's say, some more governmental or industrial alliances or standardization bodies, is very open, is international, and talking about exactly the protocols that run the internet. That there is no membership fee or a complicated way of participating, or only two per company are allowed to participate, etc. But everyone can just participate. Very simple communication, email plus meetings. So, and the key idea is reflected here in this: we reject kings, presidents, and voting. We believe in rough consensus and running code. That was one of the key ideas. Means, okay, we don't need these hierarchies. We don't need some kind of a political discussion and then voting for this or that. We just say, okay, have a good idea, implement it, show that it works, and a rough consensus that, okay, that's a good way to go. So that's the basic idea. And also, this should be only one global internet, and it's an open process. Okay, so you see, especially if you start comparing this with other standardization bodies, that's different paradigm behind it. So it's not this, the core idea is not that this is all driven by industry or all by governments. Although we have to say industry is heavily involved, and many of those standards, the RFCs, are produced also by industry. And in former times, it was a bit more academia, and there's also discussion going on who's really influencing what, and what happens if someone comes up with an idea that is not standardized, but is powerful enough to push through the idea. We have examples for this. Big companies come and say, oh, we think this is a good idea, and then trying to push through the ideas. Okay, but that's the basic idea. IETF itself is structured into different areas, like applications real-time or operations management, like routing, transport, etc. So roughly reflecting not only the layers, but also the additional areas like security, for example, something you need for all the different layers. Then you have many working groups that are rather short-lived. They focus on a specific problem. So, okay, how do we do this and that in the domain routing or whatever? You have a charter that defines the work, and when actually the work is finished, and if you're interested, please join. That's very simple. And the idea is the product then at the end is a internet draft or an RFC. So that's the result. And then there's some additional support for the organization. So what does it mean, a RFC or a draft? If you come up with a new idea, any one of you can write an internet draft. So you can write a draft, it follows a certain format. You can all look this up, and you have a good idea, you write this, and then people start discussing this draft. And it automatically expires after 6 months, but you can then change it and add something, etc. And the key idea is, if enough people agree, this draft will later maybe become an RFC. RFCs, not all of them are standards, some are just, best practices, etc. But they may become some standard. And then they're officially published, and then everyone can refer to these standards, and everything is publicly available for free. That's also different to some other standardization bodies. Sometimes you have to pay a fee, and sometimes this fee is, quite high. So there are some standards you have to pay 10,000 and more euros or dollars to get the standard. So because those bodies, they refinance themselves via selling the standards. So how does it look like? You have the document. You can all look this up. There, you see the URL, datatracker.ietf.org. You will find all these standards, and you also find the history, which is quite interesting, because you will have a standard, and after some time, people say, okay, there is now a new one, and this obsoletes another one. And so you see the history, and you see, oh, this is again updated by this and this and this and this, and then you should look for the newest one, etc. So that's quite interesting. And also all the working group, etc. Documents, they're fully available for free in the internet. So that was a quick overview of this standardization in the world of the internet, the IETF. So coming back to the structure, I showed you the hourglass model, and I gave you the advantages, but maybe also what are the disadvantages of the hourglass model. People discussing if there's yet another narrow waist at HTTP. Can you imagine why? Why is HTTP now more and more becoming the protocol for many things? What does it mean? Other narrow waist up there. I talked a lot about standards and why we need standards, but there might be also disadvantages. So maybe it's not a good idea to have a standard. Why? When? Maybe there are no disadvantages. Then to get a better feeling how it works, have a look at IETF, but also have a look at IEEE. What are the differences? How does it work? What can you access? You will see that you can access many things, but not everything when you look at the different bodies. What about 3GPP, Wi-Fi Alliance, Bluetooth Alliance, etc.? So there are some major differences.